together, let's complete a takeoff performance chart for the Piper Warrior 2 or the PA28-161 aircraft. Firstly, in New Zealand, every runway and light aircraft is assigned a group number rating between 1 and 8 based on the distance available for the runway and the takeoff and landing performance for the aircraft. If the group number of your aircraft is found, the group number for your aircraft, it can be found in your flight manual. And if the group number for your aircraft is greater than the group number or the group rating for your runway, then you need to complete a performance chart to determine if your aircraft is capable of taking off or landing on that particular runway. If it's the opposite way around, so if your aircraft's group rating is less than the group rating of the runway, then it's safe to operate that aircraft on that given runway. So to start, I've copied some information from my Automatic Terminal Information System, or ATIS, for my local aerodrome. This is our outside temperature, our QNH, which is our atmospheric pressure adjusted to mean sea level. We have our aerodrome elevation. We need to calculate our pressure altitude, and we have a represented headwind here as well. Not a represented headwind, sorry, a represented a wind. So we've got a wind speed and a directional component as well. We don't have a headwind just yet. So we first have to calculate what our pressure altitude is. So this performance chart can be broken up into 3 different components. I'm just going to erase that. Our first one here is our pressure altitude. Here is our weight, and here is our wind, and these 3 parameters are going to determine our takeoff distance in this example for our aircraft given the conditions that we're operating in. So coming back here, and if you do need one, grab a calculator. We're going to first subtract our QNH against our international standard atmospheric conditions, and the QNH for that is 1013 hectopascals at mean sea level, I believe, and 15 degrees. So 1013 minus 1030, and we won't worry about adding or subtracting at the moment, because we're going to think about what these numbers represent to determine whether we add or subtract this from our aerodrome elevation to calculate our pressure altitude. And so that's going to give us 17, and we multiply that by 30, which gives us 510. And so you might be wondering, where does this 30 come in? This 30 is our standard pressure lapse rate of 30 feet per hectopascal. So we've just calculated here our I suppose our change in pressure measured in hectopascals. And so for every 1 hectopascal that changes, the pressure change, we can expect a 30-foot increase or decrease for our effective aircraft performance at our standard, at what altitude our standard conditions would be sort of modeling, I suppose. Hopefully that made sense. So that gives us 510. And our aerodrome elevation is at 305 feet minus 510, which is a number less than 0. It's a number less than our mean sea level. So we are not going to go below 0 because we don't have any data calibrated in our flight manual here below this line that I've just drawn. So if our pressure altitude that we calculated is below 0 and our aircraft will be performing really well, we still can't draw any lines underneath this bottom line because we don't have any data that's been calibrated. So we're going to assume mean sea level, or our sea level altitude for that part of the calculation. So before we move on, let's just assume that our performance is worse. So if our QNH, our air pressure is, let's say, 1010 hectopascals, and we subtract that, we'll find a difference of 3. We multiply that by our 30 foot per hectopascal pressure lapse rate, which gives us a 90 foot change to our altitude, our aerodrome altitude. So we add that to 305, and that will give us 395. So we can expect worse performance when our QNH or our atmospheric pressure adjusted to mean sea level is lower than what the standard conditions are. And that makes sense as well, because if our pressure is lower, then we've got less air particles that will turn as the wing as they move over the wing. So we're going to generate less lift, and you can apply that same logic and reasoning to thrust generated by the propeller, as well as combustion in the engine. And so that's why we have to increase the that's why we get an increased pressure altitude when we do this calculation, because we'd be taking off in conditions that are worse than our standard conditions. So hopefully that made some sense. If it hasn't, there's a really, really good video. I've got it up here actually. It's by Flight Insight. It's just look up pressure altitude versus density altitude, and it's explained really, really well there. So once we know this, we've calculated our pressure altitude and it's below 0. We're just going to assume sea level. Our outside temperature is 3 degrees. So we're going to get a ruler and we're going to draw at what looks like about 3 degrees a line upwards to intersect. Not what looks like about 3 degrees. What is 3 degrees? You've got to be quite accurate with these things, but in this video I'm not going to be. And once we've done that, where these two lines intersect, we can draw a horizontal line over to our weight section. I'm going to assume that the takeoff weight for the aircraft is 2,100 pounds. But you can calculate this doing your weight and balance, which we're not going to do here. Again, we're going to run into another issue where we've got no calibrated data below this bottom line. So we have to we actually have to base our calculation on this, because I think this is a sort of best case scenario where we've got data to back it up, and we can draw a line following this, following that line, I suppose. Draw a horizontal line to our headwind section. So a few things about our headwind. I've got this little chart here which will help us. So if we're taking off on a particular runway, you'll have a component for headwind and you'll have a component for your crosswind, I suppose, or your wind perpendicular to your plane, and both of those make up your represented wind from a certain bearing, I suppose. So here we can use this chart to calculate our headwind component. I think I wrote down 30 at 7 knots. And if we're taking off on, if you're using, you've got a runway pair 22-4 at my local aerodrome. If we use runway 4, we can subtract 40 from 30, which gives us 10. So we're going to be working along this 10 line here. And you really should be using a ruler for this also. So actually we will use a ruler. It's good practice. And you can draw a line down to the center. And then these inner sort of circles is your wind velocity in knots here. This is your angle between the wind direction and the runway in degrees. So our wind direction is coming from 30 and we're taking off on runway 4, which is positioned at 40. So there's a 10 degree difference there. So we come down to where 7 knots would be. So we've got 15, 10, and 7 would be probably around here. And if you draw sort of these two lines, you can break your wind component into your perpendicular component and your parallel component, or your headwind component. So that sort of actually looks more like 8, and you're not going to have a larger parallel component than what the actual headwind is, and it's just because I've drawn this wrong. So we're just going to assume it's 7 and 1 knots, but we'll assume it's 7 in this case. Although, just thinking about that, saying that out loud, that would give us better performance if we have a larger headwind, and we do want to think about if we're unsure because we've done we've calculated our perpendicular and parallel components wrong, then what we might want to do is actually assume 6 knots or do the calculation properly. So a worse case scenario that'll give us a worse performance. So now that we know that it is 7 knots, what we can do is come back to our blue pen. We've got 5, 6, 7 here, and draw our line up. We want to sort of interpolate between these lines. That's quite shocking. It's probably not as shocking as my breaking that headwind up into different components though. And if we draw out here, we'll get a takeoff distance of 1,200 feet above a 50-foot barrier as well, which says that here. So that 50-foot barrier, that just looks like this here. So as the aircraft's rolling down the runway and passes that barrier, from our start to our finish, we can expect a 1,200 foot distance, the takeoff distance that will need to be required to clear that 50-foot barrier. So a few more things before we finish. We have surface types, so different runway. What would you call them? Surfaces. It's in the name actually. Different runway surfaces will also impact your takeoff performance. So The runway I usually use is a paved runway, but if you're using a grass runway, you want to multiply your takeoff distance by 1.14. If you want to convert this into meters as well, we can divide by 3.281. So 1,200 divided by 3.281, or 365 meters. And again, 365, if you times that by 1.14 for a takeoff, don't worry about the landing because we're not doing a landing performance chart. Then we get a value, then we get a takeoff distance of 416 meters. So that's how you can adjust your takeoff distance based on the surface type. And lastly, before we finish up the video, is your uphill or your downhill. So we don't want to worry about our landing distance. We're only worried about our takeoff, and depending on if you've got an uphill or a downhill slope, if you've got an uphill runway, then you have to takeoff distance correction. You add 5% to your takeoff distance, and if you've got a downhill runway, you're going to subtract 5% for a 1% slope. If it's a 2% slope, it's 10%. If it's a 3% slope, it is 15%. What happens if you're reading your AIP plate and it's 0.7 U, for example? We'll go 5% times 0.7 is 3.5. So we would add 3.5%. And that's how you can calculate that little bit extra based on the type of runway that you're using, or the slope of the runway that you're using. So hopefully you found this video interesting. We never actually looked at this AIP plate, so don't worry about it. If you've got any comments or questions, please leave them in the comments. I'm still learning this, to be really honest. So this is my understanding at the moment of how you can do a takeoff performance chart for this particular model of aircraft. If there's anything I got wrong, please let me know, and I'll be happy to discuss it or fix it. If you've liked the video, let me know. It tells me that you want to see more videos like this, and yeah, let's see. I'll continue to sort of document my learning process as I feel. I'd like to make a few more video documents or documentation to show it, because I quite like this form, but it does take a little bit more effort for me to actually produce. But hopefully it's made some sense. I'll also link a very useful document that actually talks about doing a P chart. It's a New Zealand it's by the Civil Aviation Authority, and it's just called Takeoff and Landing Performance. It covers the factors, it covers different considerations, and then how you can determine your performance. And to be really fair, it probably explains it a lot better than I did, but sometimes having it walked through visually, I know, can help. Maybe if there's a few gray areas that you have, it might be beneficial to somebody, if not myself, to be fair. It's just extra practice for me. So if you've made it this far, thank you for watching, and hopefully we'll see you in another video soon.